Yeah, they don't, well, anyways, the working computational definition, the version or versions to actually compute with. So this is when your curve is parameterized by R, 2 or 3 dimensions, and you get that the curvature at a point given by whatever t is ends up being the magnitude of R prime at t crossed with R double prime of t divided by the magnitude of R prime of t cubed. Notice the switch to a t. This allows you to compute curvature using any parameterization you want. You will get the same value out. These two are the same. The difference between them in this form, very hard to compute. But this form, I don't know if I would say easy, but it's definitely easier than working up above. So this is easy, relatively speaking, to compute. There is another form if the curve is actually along a function. So similar to the one that was on the test. And then curvature is defined at a point along that function k of x, I guess we do. And this works out to be absolute value of the second derivative of x divided by 1 plus square f prime, and then raise this to the 3/2 power. So this is in the special instance that the curve basically can be parameterized tf of t. Yeah.
What's the magnitude of f double prime?
F is just a regular real valued function. So not a vector. So I would use this, for instance, if the curve I was looking at, say, was along y equals e to the minus 3t from 1e to the minus 3 to, let's say, 3e to the minus 9. This is along a function. Instead of having to parameterize the curve, I could just tell you curvature by directly plugging in. So y prime is minus 3e to the minus 3t, y double prime is 9e to the minus 3t, and I could tell you then that the curvature at any point x would be given by absolute value of 9e to the minus 3x over 1 plus this guy squared to the 3 halves. Absolute value of the top, you can just basically remove it. E raised to anything's positive. And this would simplify down in here to be 9e to the minus 6x. So it's a different formula. If you wanted to use this formula, then you would parameterize this. T would be the x component, the y component would be e to the minus 3t. Okay? The other thing I need to be careful with is if your curve is two-dimensional, your r and your r prime are two-dimensional, and cross products are only defined for 3 dimensions. So if your r was something like, let's say, t cubed t to the 4th, just trying to do something that's easy, so that r prime here is 3t squared and 4t cubed. When I go do r prime crossed with r double prime, because I need the next derivative, I can't cross these as written because they're in 2 dimensions. So what I would really do is add a 3rd component on, but the 3rd component will be 0. So if you're computing using this formula for a 2-dimensional curve, and you're given a 2-dimensional parameterization, you go to mess with the curvature definition. Just throw zeros in for your z. Okay? Okay, now, we showed last time, however far away that was, that the curvature of a circle of radius r is 1 over r. So I worked this out. Parameterize a circle around the origin of radius r. And you can check your notes. I worked through it and we came up with this. Okay? Trying to look at a couple of other problems. So if I take a look in the book, page 753, if I look at problem 8, they give you a function here for cosine of t, t for sine of t. Now, as for what this looks like, most of the time in 3 dimensions, I don't stand a fighting chance of being able to tell you. But please notice that if that y component was 0, the x squared plus the y squared, the x squared plus the z squared would be 16. I'd have a circle of radius 4. What this t does is take that circle of radius 4 in the XZ plane and stretches it along the y-axis. So this parametrized would give you a spiral along this axis, up and down. Okay? So what I'm seeing is you push it back into the XZ plane, and the x squared plus c squared is 16. That's a circle, but you're pulling it along the y-axis by introducing that t. Yeah.
Would it have flat ends, or would it be round like a circle at the ends?
Oh, it's gonna just keep going infinitely, because I don't have any restrictions. But think of it like a slinky, you know, and if I set up a beginning and an end for t, it would be just like that slinky, okay? And if you collapsed it all in on itself, let t equal 0 in the middle here, that's when you've just got a circle, okay? So if I were to compute curvature here, using this, I need r prime. I need r double prime. I need to cross these two and then take their magnitude. Well, let me begin just by doing r prime crossed with r double prime. So minus 4 sine of t, 4 cosine of t, minus 4 cosine of t, 0, and then minus 4 sine of t. And take the cross product. So when I do that, I'm going to get minus 4 sine of t for the I component. For the j component, I have 16 sine squared minus a negative 16 cosine squared. That's going to total up to be 16. But it's the j component, so it gets a negative. And then the last component is going to be 4 cosine of t. Okay? I need magnitude of this. To get curvature, so that's going to be square root of 16 sine squared of t plus what, 256 plus 16 cosine squared of t. The same stuff, 16 pops out of the sine squared plus cosine squared. And so this is going to end up being the square root of 2, 6, I'm doing is getting out the numerator for my curvature. Okay. For the denominator, I need the magnitude of r prime, and I need to cube it. So the magnitude of r prime. So I'm going to go and do the 16 sine squared and the 16 cosine squared, add them up and get 16. And then add this in and get 1. And so this is going to work out to the square root of 17. Which means curvature at any point is the magnitude of my r prime crossed with r double prime over the square root of 17 raised to the 3/2 power. In particular, it's constant, which is not real surprising given what this spiral looks like. You know, I'm not stretching it farther in some places than in others. Now, if I change this t to a 2t, it would change what that constant was. But as it stands, you know, this is just a typical computation of curvature. So you can look back in your notes, and I did this circle of radius r is 1 over r. Instead of just redoing it, this was a problem in the book where it says compute curvature. The formulas that I used here, in particular this one and this one right here, are not formulas that you need to memorize. If you are asked to compute these, I will provide them. If I forget to provide them, then you ask. You know, let me know, because there's no need to memorize these. Okay? You can check to see that you get a 0 out. If you look at parameterization of any line, you can work it through. Okay? So, questions? Questions?
When taking the cross product, the I component is just what you get. It's minus the j and then plus the k.
Yeah.
Would that not be a plus, or I mean a minus 4 cosine?
No, because there's 0 minus the negative.
For what, the
For
K?
the k
For the
component?
K, I'm gonna go 0 minus,
Oh, okay.
yeah. And, you know, frankly, with these guys, because I'm doing magnitudes, you even get to be wrong on some, you know, up to a point, because I would square. Okay? Okay. If I look at, yeah, at T, okay. If I look at T and I take its magnitude, that equals, I put this on exams. Yeah, I think it's on the study guide for the next exam. I put it on study guides and then done this and watch people foul it up. Do you remember what you call this?
That's the The unit tangential vector.
Unit tangential vector.
What?
Nice.
Unit. That word means something. Okay? So what this does is, amongst many other things, T parameterizes a path on the unit sphere. Because T always has magnitude 1. So whatever T is doing, I've got this nice sphere, and T is a path that's always sitting on it. Okay? Any questions here? So, let me square both sides, and square of 1 is 1. If my T has an X component and a Y component and a Z component, which I'd make 0 if I was doing this in 2 dimensions, then what happens when I square the magnitude of T? I would get X prime of T. I'm sorry, I'm just squaring T, so it's sitting there. So I would get X of T squared plus Y of T squared plus Z of T squared equaling 1. I mean, all I'm doing is, if this is my T, then 1 here. This adds up to 1. Well, this is a dot product. What is it dotting? This is the same thing as T dotted with T equaling 1. Bugs me 'cause it doesn't look like a 1. I mean, what's T dotted with itself? It's X times X, X squared, plus Y times Y, Y squared, plus Z times Z, Z squared. This is why on the test, if you have 2 vectors that are pointing in the same direction, their dot product's positive. Just a slight generalization of this case. Okay? Let me differentiate this with respect to T. So basically, I want to differentiate my X squared plus Y squared plus Z squared equals 1. These are all functions of T. This would give me 2x of T, chain rule, dx dt. plus 2y of t times derivative of y with respect to t plus 2z of t times dz dt and that's equal to, what's the derivative of 1? 0. So it's an implicit differentiation. Is this okay? This is a dot product as well. I can divide through by 2, so you can ignore the 2's, but what's left is a dot product. This is really the dot product of what with what?
T and T prime.
T and T prime. T is x, y, z, and T prime is x prime, y prime, z prime. So this says that T dotted with T prime is 0. So this is what I was alluding to earlier. You have a path that's on the unit sphere, or really any sphere. Automatically, its derivative is orthogonal to the original vector. Okay?
Yeah, can you say that one more time?
Well, I'm gonna try and summarize here.
Thank you, sorry.
We start with R. We can differentiate it. But the observation is that R dotted with R prime might be anything. Might be 0 or something positive or something negative. We define T of t, T of little t, to be R prime divided by its magnitude. Unit tangential, it's length 1. It has the same direction as R prime. But its length is always 1. And if you looked at, for some reason, R dotted with T, all T is a multiple of R prime. So that might be 0. Or a positive number, or a negative number as well.
R with T prime would be 0. R with T prime would be 0.
Not R with T prime. T with T prime. T is a multiple of R prime. So we showed, or I showed, T dotted with the derivative of t is equal to 0. These two guys are orthogonal. What's the length of t prime? Well, I don't know. Not necessarily 1. We define the unit normal direct vector and the normal to be the following. It's a unit vector. Its length is always 1. It's a multiple of t prime, so we have that the magnitude of n is always 1, and n dotted with t is always 0. Okay, so let me draw the pictures that are relevant. Comment number 1 is you don't ever want to compute n. It's obnoxious enough to compute t. You're going to have a square root in the denominator due to magnitude. To compute n, you'd have to differentiate your t and then divide by its magnitude. This is really obnoxious. You don't want to go through the bother of computing these, nor do you need to. Okay? Before I show you the relevant stuff here, let me first make sure you understand what's going on. If I have a curve parameterized by r, so r parameterizes my curve. This could be in 2 dimensions or 3, but I'm gonna just draw it in 2 because I stand a fighting chance. So let's make the direction look like this.